Okay, in this assignment, we're supposed to create velocity time graphs and acceleration time graphs from this data that's plotted out here, that's on the data table on the left-hand side. So we need to go to our mnemonic. Remember our mnemonic? We write out like this, x, VA, and in this direction, we find the slope. In the opposite direction, we find the area. So since we're using a position time graph and we want to find the velocity and acceleration time, we need to find the slopes of the different segments of this particular graph. So if we look at the different segments, notice we've got this part that's parabolic, so that's sort of separate. That's its own separate segment. Then we've got this next part here that's linear. So from that point to that point's linear. Then from here to here, we find that this has got a particular shape, so that's its own segment. Then we've got another segment here, from there to there, and then another segment from there to there. So we need to break it up into those different parts. So there's a part from 0 to 2 seconds, from 2 to 4 seconds, from 4 to 8 seconds, from 8 to 10 seconds, and from 10 to 12 seconds. So our mnemonic again tells us to find the velocity from the position time graph. We need the slope if we're going in this direction. So we can't find the slope of this particular curve because it continues to change. So what we need to do is we need to use an equation. So let's go ahead and look at this from 0 to 2 seconds. Again, we're looking at it from here to here, and because there's a curve, again, we can't use a slope directly because it's not a straight line. So let's go about solving this and looking from 0 to 2 seconds using our strategy. So if we use our strategy of writing out x, v initial, v, a, and t, we find that our initial position, our total distance that we're to travel, our final position, is after 2 seconds, 8 meters. So, because again, we're going from 0 to 2 seconds, so we're at 8 meters. Our initial velocity is 0, that's what we're assuming, 0 meters per second. Our final velocity, we don't know. Our acceleration we're looking for, and we know this is going to end after 2 seconds. So what we've got to do is we've got to find an equation that has these 3 variables and the other 2 that we're looking for. So let's go with velocity and acceleration. Let's solve for acceleration first. And the equation that would have this, and acceleration would be x is equal to x initial plus v initial t plus 1/2 at squared. Right? We know that both of these are going to go to 0 because they're both 0. So if we solve this for acceleration, we get 2x over t squared. And if we plug our values in for x, that's 8 meters. For t, we get 2 seconds squared. And so we find that our acceleration is 4 meters per second squared. Now that's going to be a constant acceleration. That's our value of our acceleration. We could also find the velocity by using this equation, v equals v initial plus at. And we plug our values in. Our initial velocity, again, 0 meters per second, plus my acceleration of 4 meters per second squared, times my time that I'm going to square there, which is 2 seconds that I'm going to square. Oh, I'm sorry, it's not squared. That part is not squared. It's just 2 seconds. So I get v is equal to 8 meters per second. So this is the final velocity for this particular section. So now we're going to look at what happens from 2 seconds to 4 seconds. And remember what we said earlier. We recognize that this part is linear. So to find the velocity there, all I got to do is use the rise over run. So in this case, my mnemonic does work, so I can find the slope of this position time graph by finding the rise. My rise, at 4 seconds, I'm at 24, and at 2 seconds, I'm at 8. So my rise there is 16 meters, and my run is 2 seconds. So I get 16 meters divided by 2 seconds, or 8 meters per second, as my constant velocity during that time period. Because the velocity is constant, and I know that the acceleration is the final velocity minus the initial velocity for that segment over the time, the change in velocity is just going to be 8, because that's the final velocity during that segment, minus 8, which is the initial velocity, over a time of 2 seconds. So you get a constant acceleration of 0 meters per second squared. So that's the acceleration from 2 to 4 seconds, and that's the velocity from 2 to 4 seconds. From 4 to 8 seconds, that's from this point to that point, we notice that we've got a very specific shape there as well. So again, it's not a straight line, so I have to use my equations there. Going back to our strategy, I'm going to write x, v initial, v, a, and t. My x there, that's a total displacement from 4 seconds to 8 seconds. From 4 seconds to 8 seconds, my total displacement is 16 meters. My initial velocity, I get that from the previous part. From the previous part, I remember that I had 8 meters per second at the end of 4 seconds. So that's the same velocity right there, 8 meters per second, as it was all through here. So it was 8 meters per second all through this part right here. So that's the initial velocity for this segment that goes from there to there. So I can write down 8 meters per second. My final velocity I do not know. My acceleration I do not know. But I do know that that goes from 4 seconds to 8 seconds. So that's a total of 4 seconds. So using this equation again, I can solve that equation. It boils down to, if I solve that for acceleration, I get 2 times x minus x initial minus v initial t. And you might wonder where this part comes from. That's the final position minus initial position for that segment. So that was 40 minus 24. So 40 minus 24. So again, that's where we get that 16 meters. Okay, so that equals 16 meters. And I'm going to divide that by t squared. So my acceleration is equal to 2 x minus x initial, we said it was 16 meters, minus the initial velocity. So the initial velocity was 8 meters per second. 8 meters per second times the time of, this is the time from 4 to 8 of 4 seconds. And I'm going to divide that by the time of 4 seconds squared. I get an answer of negative 2 meters per second squared for that section from 4 to 8. From 4 to 8 seconds. So that's my acceleration. And then once again, I go to this equation to solve for my final velocity for just this section. I get v. My initial velocity is the initial velocity that I got from the previous section. That's still 8 meters per second. Plus my acceleration, which I know now, is negative 2 meters per second squared times a time of 4 seconds. So this comes out to be, my final velocity for this segment is 0 meters per second. So my final velocity for this segment is 0 meters per second. My acceleration is negative 2 meters per second squared. From 8 seconds, which starts from right there to 10 seconds, I get this shape that goes like that. That's parabolic. Again, it's not linear, so I have to once again use my equations to figure out the acceleration and final velocity for this section. So for the strategy, I'm going to write x, v initial, v, a, and t again. My change in my position, it's always, remember, that's always final position minus initial position. So we went from 40 at 10 seconds, or we went from 38 to 40. So I'm going to take 38 meters minus 40 meters, and I'm going to get negative 2 meters. So we started off at 40, went back to 38, so that's why I got a negative 2 meters there. My initial velocity is initial velocity from the previous part, which we figured out to be 0 meters per second. My final velocity is what I'm solving for, so is my acceleration. I know the time for this period is just 2 seconds, because I'm going from 8 to 10 seconds. So once again, I got to solve for my acceleration using my acceleration equation. And my acceleration equation, if I take this part to it, let me solve it a slightly different way. I'll just plug all my values in. So I'll plug in 38 meters as my final position. That's going to equal 40 meters plus v initial, which is 0 times the time of t plus 1/2 at squared. A t squared, and I know the time is once again 2 seconds, and I'm going to square that. So I get over here, if I subtract 40 from both sides, I get negative 2 meters. That becomes 0, and I get 1/2 2 squared. So 4 times 2 gives me 2 seconds squared times the acceleration. So that gives me acceleration of negative 1 meters per second squared for that interval. Then the final velocity for that interval, right there, the final velocity for that interval, I would use, once again, this equation. V is equal to V initial. My initial velocity was 0 meters per second. My acceleration is negative 1 meter per second squared times a time of 2 seconds for that region. So I get a final velocity of negative 2 meters per second. So for this section, the final velocity is negative 2 meters per second. The acceleration is a constant negative 1 meters per second squared. From 10 to 12 seconds, that's from this region to this region. Once again, I have a parabolic shape, so I can't just calculate the slope. I've got to use this equation again. So let's do that. X, V initial, V, A, and T. So for X, I'm going to plug in, I go from 38 to 36 meters. So my final velocity, our final position is 36. I'm going to subtract 38, and that gives me negative 2 meters. My initial velocity, which I would get from the previous problem, from the previous velocity, my initial velocity is now the final velocity for the previous section. So it was negative 2. So here it's negative 2 meters per second. So right there is negative 2 meters per second. That was the final velocity for this section, but is the initial velocity for this section. My acceleration is what I'm looking for. Same with the velocity. And again, this is taking 2 seconds. So if I plug this into my equation of x is equal to x initial minus v initial t, I would get 36 meters is equal to 38 meters plus v initial, which in this case is negative 2 meters per second times the time of 2 seconds. I'm going to run out of space here. I'll put it down here, plus 1 half a, which I'm solving for, times t squared, 2 seconds squared. So I get, if I subtract both sides by 38, I'll get negative 2 meters on this side. Negative 2 times 2 is going to give me negative 4 meters. I'm going to get that there. And then over here I'm going to have plus 1 half a 4 seconds squared. Okay, so if I add 4 meters to both sides, I get a positive 2 meters over on this side, and that's going to equal 2 seconds squared times a. So a is going to equal 1 meter per second squared. So that's my acceleration for that section. My final velocity, again, I'm going to use this equation here, v equals v initial plus at. My initial velocity, again, is negative 2 meters per second. That was the final velocity for the previous section. The acceleration we just calculated out is 1 meter per second. And the time is 2 seconds, because it's taking 2 seconds to get from 10 to 12. So my final velocity in this case is going to be 0 meters per second. Okay, to wrap this up and make our velocity time graph, I want to point out one thing to begin with. First of all, the acceleration, the beginning acceleration should not be 0, because we proved that that actually is 4 meters per second squared. Okay, so let's break this up into the different sections. From 0 to 2 seconds, we found out that this acceleration, this 4 meters per second squared acceleration, was constant throughout. Okay, and the object went from 0 meters per second to 8 meters per second. Right, then from 2 seconds to 4 seconds, we found out that we had a constant velocity of 8 meters per second, and since the velocity was constant, the acceleration should be 0 meters per second squared. Then we looked at the time frame from 4 seconds to 8 seconds, and from there we found out that the acceleration was a constant negative 2 meters per second squared. And the final velocity at that point was 0 meters per second. And then from 8 seconds to 10 seconds, we found out that there was a constant negative 1 meter per second squared with a final velocity of negative 2 meters per second. Then from 11 to 12 seconds, we found out that there was a final velocity of 0 meters per second with a constant acceleration of 1 meter per second squared. So if we were going to graph this, we would start off at 0, 0 for the velocity. And then that gets up to 8 meters per second after 2 seconds. So we would have this straight line first. Then we set a constant velocity from 0 to 4 seconds. Like that. And then at the end of 8 seconds, we were supposed to be back down to 0. So we go down from there to there. And then at the end of 10 seconds, we're supposed to be down to negative 1. So at the end of 10 seconds, we're supposed to be down to, negative 2. So from there to there. And then finally, at the end of 12 seconds, we get to 0 meters per second. So that's what our graph should look like on the velocity time graph. Now, using these values for the acceleration, let's graph the acceleration. We found out that our acceleration should look like this. For the first 2 seconds, we should have a constant 4 meters per second squared of acceleration. Then from 2 to 4 seconds, there's no acceleration, because remember, it was a constant acceleration. Then from 4 to 8, we had a value of negative 2 meters per second squared, which will go right there. Then negative 1 meter per second squared, which would be right there. And then a final acceleration from 10 to 12 seconds of positive 1 meter per second squared. So that's what our final acceleration time graph would look like. All right, now what we need to do is draw a velocity time graph and a position time graph from this acceleration time graph. So what we'll do is we'll start this off by looking again at our mnemonic. Remember what our mnemonic says? Our mnemonic says that if we write it out XVA, if we go in this direction, we need the slope. If we go in this direction, we need the areas. So obviously what we're doing in this particular setup is we're going to find the areas because we are going in this particular direction. We're starting off with acceleration and we want to find out the velocity. So we start off by going from 0 to 2 seconds and looking at this particular area. Okay. All right, so we can block this off in its different sections. This section here has its particular area, and this has got a particular area, and right here there's a particular area. There's also an area here too, but we probably recognize what that area should be already. Now let me get a different color pen here, and this area here has a base of 2 seconds and a height of 4 meters per second squared. So 4 times 2 is going to give me 8. And if I use the correct units, that would be 8 meters per second. And this section, obviously, we notice that that's 0 meters per second. In this section, I've got a base of 4 seconds and a height of -2 meters per second squared. So -2 times 4 gives me -8 meters per second. And then in this next section, I've got a base of 2 seconds and a height of -1 meters per second squared. So 2 times -1 gives me -2 meters per second. And likewise here, I've got a base of 2 seconds and a height of 1 meter per second. So that gives me an area of 2 meters per second. So these are the values we will be using. So what we always do is we always take the previous value and we and we add on the later value. So if I look at a graph of this, if I'm going to calculate out the time in seconds and the velocities in meters per second, at time is equal to 0 seconds, my velocity is supposed to be 0. After 2 seconds, right here, after 2 seconds, I should have been going 8 meters per second squared. So after 2 seconds, I should be going 8 meters per second. Not meters per second squared, just 8 meters per second. Then here, after 4 seconds, I would add the previous two, the 8 meters per second and the 0 meters per second. 8 and 0 still give me 8 meters per second. And then after 8 seconds, when I get to that point, 8 seconds, I would take the -8, I would take the 0 and the 8 meters per second, add them all up to get me 0 meters per second. And then after 10 seconds, I would add all previous values. The -2, -8, 0, and 8 would give me -2 meters per second. And finally, after 12 seconds, I add up all of these values, 2, -2, -8, 0, and 8, and that gives me a final velocity at the end of that section, excuse me, of 0 meters per second. So if I graph this out, after 2 seconds, I'm supposed to be at 8 meters per second. 2 seconds, I'm supposed to be here at 8 meters per second. I started here at 0. So these are all constant acceleration, so these should be straight lines. Then after 4 seconds, I'm still at 8 meters per second, so that was a constant 8 meters per second. After 8 seconds, I'm supposed to be down here to 0, so I'm going to draw a straight line from there to there. Then after 10 seconds, I'm supposed to be at -2, so would look like that. And after 12 seconds, I'm supposed to be back at 0. So there's my graph of the velocity time graph from the acceleration time graph. Then I take my velocity time graph, which is redrawn here to make it look a little more accurate. I would do the same thing here. I'm going to take these areas and I'm going to add them up to get the acceleration. Because remember, from our mnemonic, XVA, when we go in this direction, so we went in that direction, now we can go from there to there, we need to take the areas. So this particular area from 0 to 2 seconds, it's 1/2 base times height. Okay, so my base is 2. My height is 8 meters per second. So 1/2 base times height. Let me write that down here. 1/2 base, 2 times 8 is going to give me a displacement of 8 meters. Then from here to here, I've got a base of 2 seconds again, but a height of 8 meters. So this area for this rectangle is 16 meters. Then this next rectangle is 1/2 base times height. Once again, so my base is 4. So 1/2 times 4 times 8 is going to give me 2 times 8, 16 meters once again. And 1/2 base times height for here, my base is 2, my height is -2, so 2 times -2 is -4. I divide that by 2, so I'm going to get 2 times 2, so -2. I'll write that, -2 meters for this section. And then for this section, once again, a height of -2, a base of 2, so 2 times 2 divided by 2. So this area will be still a -2 meters. So if what I've got to do is I have to add all previous areas to find this total, my total displacement. So if I write out a graph of time in seconds and displacement in meters, I'm starting off with 0, 0. I know after 2 seconds, I've gone a total of, let me use a different color here. I'm going to go a total of 8 meters. So I will put 8 meters there. Then after 4 seconds, I add up all previous areas. So 8 meters plus the 16 meters gives me 24 meters. Then after 8 seconds, right here, 8 seconds, I add up all previous displacements. So 16 plus 8 will give me 40 meters. And then after 10 seconds, I'm going to take -2, 8, 16, 16, and 8. After 10 seconds, I'll be at 38 meters. Then at 12 seconds, I add up all previous, or I should say now the total, -2, -2, 16, 16, and 8, to get a total of 36 meters. And that's what I'm going to graph out. So my graph, I'm going to graph, so at 0, I'm down here at 0. At 2, I'm at 8. At 4, I'm at 24. At 8, I'm at 40. At 10, I'm at 38. So somewhere around there, I guess. And then, oops, notice I missed a spot right there. And then at 12, I'm at 36. So this is kind of off a little bit right here, if you'll notice. I missed a spot. So the actual graph, when you're done with it, so this is all okay. Your graph, when you're done, should look like that.